Hi everyone, this is Madison here to talk about the proofs for Kepler's second and third law. So to start off, I was just going to review Kepler's laws in general. The first law states that a planet revolves around the Sun in an elliptical orbit with the Sun at one focus, as you can see here in this diagram. This is the Sun at the focus of the ellipse. The second law states that the line joining the Sun to the planet sweeps out equal areas in equal times. So what that means is that both these A's will be equal if the time it took for the planet to go from here to here is equal from the time it took from here to here. The third law states that the square of the period of revolution of a planet is proportional to the cube of the length of the major axis of the orbit, which is stated here. It's proportional because these are all constants minus the a cubed. Okay, so to start off by proving Kepler's second law, we'll follow these 4 steps as outlined in the textbook. Okay, so the first step, these are the previously established equations that you need to know before beginning. So r equals r cos theta in the I direction and plus r sine theta in the j direction. And then h equals r cross v, and v is the derivative of r, so it's velocity and position. Okay, so step 1, which is what we're doing here. So first you have to parameterize the r vector, so it becomes the x equals r cos theta and the sine equals r sine theta. So then you find the derivative of r, and from there you can do r cross v, because recall that r prime equals v. Okay, so once you perform the r cross v, which equals h, you get this whole mumbo jumbo, and then once you simplify the z coordinate, you can say that the h vector equals r squared d theta with respect to dt in the k hat direction. Okay, so step 2 is basically just saying that the vector h, the absolute value, is equal to h, so it becomes a scalar rather than a vector. So you can take away the k, which indicates direction, and leaves you with this, h equals r squared d theta by dt. Okay, so for step 3 there are also some equations that you need to know before you begin. The area of a circle equals a 2 pi r squared. So then from there we can make our approximation where we replace pi with d theta here, but to accommodate for the 2 we have to multiply by half so that they're equal. So our approximation is equal to half r squared delta theta. Okay, so then we integrate with respect to theta, and it pops out that dA over dt equals half r squared d theta dt, which is what we were wanting to get. So the final step is to prove, as you can see up here, dA by dt equals half h, which is a constant. Okay, so we take these equations from step 2 and from step 3, and then we combine them and rearrange to find that dA over dt equals half h. So this is only half of what we were supposed to do. We still have to find that h is constant. So to do that, we need to recall from before that the h vector is equal to r cross v. So from there, we can find the change in h, which ends up being 0, because these are parallel vectors, and anything crosses something that's parallel is equal to 0. So now we have proved that the change in a with respect to time is a constant, which is exactly what Kepler's second law states. Moving on to proving Kepler's third law. These are the steps that we're going to follow to prove the law. I'll let you read them there. And the law, just as a reminder, the final product that we're looking to get is that t squared is directly proportional to a cubed. Step 1. Okay, so we first need to know the area of ellipse, which equals pi ab, and a and b are just the major and minor axes. If there's not a 2, it's the semi-major and minor axes, which just means half of that. Okay, so from there we can separate. This is an equation that we had previously. We had previously worked out in the last segment there. So then we integrate with respect to a on the right side with respect to t on the left side, and we get a equals half ht. And the capital T here is the period of revolution. And when we were integrating, we had to have the period as the upper bound so that this equals t, because it would be t minus 0 equals t. So now we have our equation that we were looking for. Step 2. We want to prove that all of these are equal. So all the equations that you need to know before you start this step are listed at the top here. And basically you just substitute in and simplify, and you get ED equals ED equals ED. So check, we proved that this is true. Okay, step 3, the final step, is just to combine the first two steps. This is the equation we received from the first step. It's a bit modified, I squared it. And this is the equation received from the second step, also just a bit modified. And then when we plug them together into this equation, we find that t equals 4 pi squared a cubed over gm, which is Kepler's third law. So thanks for watching, and I hope it was informative.